Hi, I'm Dave Lazovsky, the founder and CEO of Celestial AI. We are the creators of the Photonic Fabric, the optical interconnectivity technology platform for accelerated computing. I'll give you a quick overview of the Photonic Fabric and then walk through some application examples where we are integrating Photonic Fabric interface chiplets with our customers' AI accelerators, both to provide compute-to-compute interconnectivity with high bandwidth, low latency, low energy optical I/O, as well as compute to high capacity, high bandwidth disaggregated memory. I'll start by going through what's driving our business. So AI is a technological and economic wave like nothing the world has ever seen. What's interesting about this market are really a few things. One is the size of it. The other is the rate of growth, which is projected to grow to approximately $1 trillion market by roughly 2032. But another thing is the concentration with 4 hyperscalers representing roughly 70% of all AI data center infrastructure, these 4 companies, all of which, by the way, are building their own silicon and their own data center architectures, including network interconnectivity architecture. AI is truly changing everything, right? So these models are growing exponentially, and the memory requirements for some of the more advanced models are outpacing the compute requirements by as much as 100x, right? So this industry has transitioned from a compute-limited regime where every model in existence just a few years ago could fit comfortably inside of the memory capacity of a single AI processor or GPU, to today where you need literally hundreds or thousands of AI accelerators or GPUs to be interconnected to be able to house a single model, even for inference. And then the training requirements are up to 10 times that. So the issue that has presented itself, as most of you are aware, over the course of the last few years is what's being deemed the memory wall. Right? So the challenge has transitioned from compute limitations being the metric being perf per watt to today the limitations for all hyperscale data center infrastructure is bandwidth. It's memory bandwidth and it's chip-to-chip interconnectivity bandwidth for the most significant operation that's running for these workloads, which is an RDMA. It's remote direct memory access. This chart here on the right outlines a projection for off-package bandwidth that NVIDIA has been sharing for the last few years. And we have overlaid on that where co-packaged optics currently lands at a single reticle limited package level. It's about 18 terabits per second of maximum off-package bandwidth. So that translates to about 2 terabits per second per chiplet for companies that are serving the space, and there are several focusing primarily on Ethernet interconnectivity for RoCE operations, companies such as Broadcom, Intel's made an announcement, IR Labs, and others. The challenge here is that the minimum bandwidth requirements for addressing the memory wall shown on the left is today HBM3E. That bandwidth is 8 terabits per second in each direction, so it's a total of 16 terabits per second bidirectionally. Most of these systems are actually limited by the NoC, the network on chip, at about roughly 80% of HBM3 bandwidth per stack of HBM. What we have created with our Photonic Fabric interface chiplets is the ability to keep pace with a full HBM bandwidth while also addressing 3 other critical metrics necessary to deliver competitive solutions here. And those metrics include power or energy efficiency, particularly for an RDMA operation. It includes cost, and that cost is measured in dollars per gigabit per second of bandwidth and dollars per gigabyte of memory capacity. And most critically, for many of these workloads, it includes latency. And for some of the workloads, including generative AI workloads or recommendation engines, having an intermediary switch in the network between the memory systems becomes prohibitive from a latency standpoint. So what you see on the chart on the right is basically two different product offerings that we currently have available in our silicon validated qualified Gen 1 technology. The first is in the form of a chiplet. And we have 14.4 terabits per second of bandwidth per chiplet currently in our Gen 1 technology. We have the ability to quadruple that in our Gen 2, which is about 16 months out. The other form factor that we have is either an interposer-based form factor or an optical multi-chip interconnect bridge, what we call OMIB, which is similar to CoWoS-L, EMIB at Intel, iCube-E at Samsung. It's a bridge technology that has both electronic as well as photonic interconnectivity functionality, enabling both within chip and chip-to-chip optical communication. So the building blocks for our technology platform are shown here. Fortunately for us, silicon photonics has become quite mature over the course of the last 15 years and increasingly over the course of the last 5 years, driven in large part by data communications, both data center transceivers and high-speed switches. We're also using state-of-the-art CMOS. In our case, we use TSMC 4 and 5 nanometer CMOS for all the transmit and receive side of the control circuitry, our SerDes and our router and switch functionality. And then again, from an optoelectronic system and package standpoint, we're using known, proven, high volume manufacturing qualified technologies that are a product of advancements in both GPUs and AI accelerators in terms of 2.5D packaging, as well as optical interconnectivity that again has been driven in large part by data communications. So to go through a general overview of the photonic fabric, what you see here in the top left is the physical layer. And what we have created is actually a full stack solution. It provides the ability to deliver data not just to the package and electronically interconnect our chiplet to a GPU or to a memory system. We have the ability to deliver data directly to the point of consumption within the chip. And that's the product of having a few elements that are highly differentiated in the overall technology platform. So if we look at each one of these photonic fabric IP blocks and we blow it up a bit, what you see in here is the full optoelectronic system. So on the electronic side, we have both the transmit, the driver, as well as the transimpedance amplifier on the receive side. What's unique about our technology is that we're building the electronics, including the SerDes and including our network convergence layer in extremely advanced silicon 4 and 5 nanometer CMOS. We're using state-of-the-art. The other significant element of differentiation is the silicon photonics. So in our case, we're using a thermally stable modulator that allows us to directly package high TDP ASICs in direct proximity to a compact, thermally stable silicon photonics modulator, which enables us basically to minimize the distance between the modulator and that modulator driver in the control electronics, and similarly on the receive side between the photodiode and the transimpedance amplifier. So because those copper distances are tiny, less than roughly 100 micron, it significantly reduces capacitance in the line, and we have very minimal ISI. So the noise level is low, signal to noise is high, bit error rates are extremely low, which allows us to eliminate the need for a digital signal processor for the full electrical link. Once you have the ability to eliminate the DSP, which our technology enables, then you have eliminated the largest both power consumer in the control electronics as well as the area consumer in our control electronics. So it allows us to achieve otherwise unachievable levels of energy efficiency for the full electrical links and world-class industry-leading bandwidth densities for the Photonic Fabric technology system. So one example of an implementation is shown here, which is our Photonic Fabric chiplet. In this case, we have bandwidth matched the Photonic Fabric chiplet bandwidth at 14.4 terabits per second to the network on chip limitations of our customers' ASICs. And here we're showing an example where we're integrating with a conventional UCIe PHY that provides both the bandwidth that supports our current generation of technology and provides scalability to up to 30 terabits per second of bandwidth inside of this form factor. We use a fiber array unit, which are running in extremely high volume production for other applications. Our supplier is shipping millions of these units per year that are all leveraging a fully automated wafer scale assembly process. So again, what you're looking at is a top-down view of the optoelectronic system with the electronics manufactured in TSMC 4 and 5 nanometer. The RDMA transport latency of this device coupled with either a matching Photonic Fabric chiplet on the other side or an optical memory module, which we have also, we're also in the process of commercializing. That transport RDMA latency is about less than 100 nanoseconds. And the energy efficiency of this link, because of the advantages that I had mentioned on the previous slide, are about 10x, 8 to 10x, depending on the implementation. So for copper links and state-of-the-art RockE, which is the RDMA over converged Ethernet, we're on the order of 10x lower in picojoules per bit for that RDMA transfer. So some of the implications of the Photonic Fabric 14.4 terabit per second Gen 1 chiplet are shown here. We use a conventional 2.5D UCIe interface. We can also use MaxPhi, for example, from Broadcom. It does unlock the ability to provide optical connectivity, electrical, optical, electrical, for AI processors, including AI accelerators and GPUs. It enables both compute-to-compute interconnectivity for scale-up backend networks, as well as compute-to-memory, including using some of the emerging protocols like UAL, with the full HBM3E and HBM4 bandwidth, without sacrificing bandwidth, latency, or power. The other thing that we have designed right into the Photonic Fabric, again, is a network convergence layer that allows us to be protocol adaptive. So we are protocol compatible with standard protocols, including JEDEC standards like HBM, like CXL, and emerging protocols, again, like UAL and proprietary protocols that our customers may have. The other nice thing is that we are directly compatible with standard 2.5D packaging flows from some of the largest ASATs, so the leading OSATs. The FAU attached technology is also fully automated and qualified in high volume production for high throughput attach. The metrics that we track are in large part shown here. Bandwidth is a critical metric, and again, having at least HBM3E level bandwidth of 8 terabits per second in each direction is a prerequisite for these applications if you're trying to address the memory wall. We're about 3.6x state-of-the-art as it pertains to optical interconnectivity. At this point, I think that's what's driving, frankly, a lot of the demand for our business is the fact that we've got HBM3 bandwidth, plus our latency, again, is roughly 5x lower than state-of-the-art, which is highlighted here. Our power efficiency from a picojoule per bit standpoint is 8x lower than proprietary state-of-the-art, which is shown here, which is Gen 4 NVLink. But we're about 10x lower than a conventional copper link and 10x lower than RockE. And a cost per gigabyte of memory, this is where there's a huge advantage, because once you have the ability to integrate a photonic link that has the full bandwidth of HBM3E, you can attack the memory wall differently. So what we are working with customers to commercialize currently is optically interconnected high capacity, high bandwidth memory. So what you're looking at here is our Photonic Fabric memory module, which has 2 stacks of HBM3E integrated with a 5 nanometer ASIC that has multiple levels of functionality, and that gets integrated into a module that has up to 4, or in some cases up to 8 DDR5 DIMMs. So in that ASIC, there's the controllers in 5 for both DDR and HBM. It also has multiple Photonic Fabric IP blocks that facilitates the bandwidth that is required for the applications, and it incorporates a low radix switch. So we have an onboard switch integrated. Effectively a memory controller, Photonic Fabric transceivers, and the integrated network switch, all integrated in each module. So we are we're working with systems integration partners to integrate these modules, 16 of them, into the Photonic Fabric memory appliance. So this provides processor to high capacity, high bandwidth, disaggregated memory. And there are several advantages here versus a conventional RoCE operation, or even state-of-the-art NVLink. If you have large models, some of our customers have models that are up to 10 trillion parameters. Rather than sharding those models over what can be hundreds of AI accelerators, here you can locate all of the parameters, 100% of them, inside of the 33 terabytes of memory capacity in our Gen 1 Photonic Fabric memory appliance, so that the memory is all directly addressable to up to 16 processors, in this case with extremely low latency and extremely low remote direct memory access latency. Now, this element of the network is complementary to top-of-rack Ethernet connectivity. We are not competing with Ethernet connectivity. This is where we believe the vast majority of chiplet-based co-packaged optics is focused, given the bandwidth capabilities of competing optical chiplets. We are focused on optical compute interconnect, which has much higher bandwidth requirements for both processor-to-processor interconnectivity, which we call the Photonic Compute Fabric. That's compute to compute, as well as the Photonic Memory Fabric, which provides, compute to memory direct connectivity via the Photonic Fabric with high bandwidth and low latency. The other advantage here is the ability to leverage the fact that there are 16 low radix switches integrated in each one of our memory modules, and the chiplets that are being rolled out for the initial implementation of the Photonic Fabric integration for our customers with our current AI accelerators provide the interface to both the memory layer as well as the routing layer for larger scale exascale systems. So in this case, what we're showing you is a 792 terabyte memory capacity system that provides up to 128 directly connected all-to-all via the Photonic Fabric. So again, a lot of innovation here that we've summarized in a relatively short period of time. For more information on Celestial AI, feel free to reach out to us at info@celestial.ai, or you can visit our website at www.celestial.ai. Thanks very much.